Okay. Hello. So, 5.7. Um, so if hopefully you have a copy of the long thing of notes that I gave the sub and told them to print you guys a big old copy of it. Kind of showing what I want you to take notes on and kind of teach yourself versus what I'm going to do video on. So for 5.7, page 354 and 355, I said I want you to just go ahead and take notes and try to learn that yourself. That really is just the same ideas that we just learned in 5.5. Now just applying it to the antiderivative of 1 over x, which would be ln x, well, ln absolute value of x. So say a couple logistical things. Obviously, we're skipping over 5.6. We just did that, like, I don't know, a few sections ago. That's the trapezoid rule stuff. The reason that we need the absolute value around the x or whatever the inside function is, it's an inside function. If you're looking at the box of formulas at the top of 354, it's just like a domain issue. Right, obviously we can only take the natural log of positive things, and if you start with a 1 over x function, if you graph it, the domain of 1 over x function is any number except 0, right? So you would have a domain that's negative infinity to 0 not inclusive, and then 0 not inclusive to positive infinity, whereas the domain of ln would only be numbers greater than 0. So that's why you have to put an absolute value thing next to the after the ln part. But you know that the derivative ln of blop is 1 over blop times derivative blop, whatever. So we're just going backwards. So that's something you should already know. It's just something we're going backwards, just like we have been doing for all integrals, aka antiderivatives type stuff. So in fact, like example number 1, I think the way they handle that is really dumb. Like, really, really dumb. Like, for number 1, why wouldn't you just factor out, why wouldn't you just pull out the 1/2 before you do anything? They try to, like, force the, chain rule pattern thing by, like, multiplying by 2 and then multiplying the outside by 1/2, but you get rid of all your problems by literally just initially factoring out the 1/2 from the integral. So the way they do example 1 is silly, inefficient. I would ignore that. The way they do example 2 is fine, right? Again, like your inside function is 4x minus 1, derivative of that's 4, so you need a 4. Notice you need a 4 in the numerator, not in the denominator. So you need a 4 in the numerator, so they multiply the integrand by 4, but then they have to multiply the outside by 1/4, so that 1/4 carries down to the final answer, and then, right, your overall outside function is like 1 over blop, antiderivative 1 over blop is ln absolute value of blop. What is your blop? Your blop is 4x minus 1. So 1/4 ln absolute value 4x minus 1 all plus c. Okay. Example 3, they're just making sure you remember that definite integrals are finding areas under curves. So they ask it a little bit differently. Your inside function is x squared plus 1, derivative of that is 2x. On top you have an x, not a 2x, but that only differs by a constant multiple. So you can plop a times 2 in the numerator, plop a times 1/2 outside. And so see, notice they do a definite integral there, but since they force the pattern and they don't go all the way to the u's, then you don't have to use u bounds. If you don't go all the way to the u's, all the way to the end, then you can still use the same old x bounds they give you. So, like, that's how I would do, whatever 90% of these types of problems, unless it just so happens to be a problem where you just absolutely, that doesn't work, right? We talked about when you would need formal substitution. Example 4 is just kind of like bam, bam, bam. examples of, again, things where the answer at the end ends up being ln of something. Basically, there's a separate section for this for a reason. It's very common that it works out that the derivative of the derivative of the denominator of the integrand is some kind of constant multiple of the numerator. It's pretty common. So if you ever see something, it's not like obvious what you would use, right? In our previous example, sometimes it was just like really obvious how you would just force the pattern. But it's just getting you used to seeing things, like for example, for A, right? That maybe on initial inspections, like, I don't know, it's just a division of two polynomials. But, right, it's getting you to think, okay, well, like there's this common idea that what if our bottom was u, right? If our bottom was u, then du dx would be 3x squared plus 1. What's our denominator? Hey, 3x squared plus 1. It's exactly the same thing. Usually it's not exactly the same thing, but hey, that one's easy. It's exactly the same thing. So then therefore, right, basically we have our u prime is right there in the numerator. And then we have times our 1 over u, right? The antiderivative of 1 over u is u to the absolute value, is ln the absolute value of u. The 3x squared plus 1 gets absorbed because that's the u prime. You tack on a c, bada bing, bada boom. Same thing with b. Again, b, if you weren't kind of already on the lookout for it, b might be really confusing. In fact, you might even try to do like weird trig stuff. You might be thinking, I don't know, maybe we write the secant as like 1 over cosine. And then like, oh, I don't know what, actually, you probably could actually end up doing that a different way, because then, no, just kidding. Because then you'd end up with 3 cosines up. No, one of the cosines would cancel. Anyways, you could do b a different way if you rewrote it. Because tan you could rewrite as sine over cosine. But anyways, even as it is, right, the derivative of tangent, the derivative of the bottom tangent is secant squared. So, do you see that pattern? Boom. So your u is in the bottom. So you have your u prime present exactly as you need it to be, which is the secant squared x that gets absorbed. What you're left with is 1 over u. The antiderivative of 1 over u is ln absolute value of u. What is u? Tan x, plug it in, plus c. Same thing for c, except for c is a little bit trickier because the derivative of the bottom is 2x plus 2, and up top you have x plus 1, right? But x plus 1, if you just multiply that whole thing by 2, boom, you got your 2x plus 2, right? So again, it's a constant multiplier of what you need. If it's a constant multiplier of what you need, you multiply the integrands by 2, you multiply the outside by 1/2 so that it's balanced out. And then, again, bada bing, bada boom. So your u is the x squared plus 2x. So overall, you have the u prime times 1 over u, antiderivative of 1 over u, ln absolute value u, so you have ln absolute value of x squared plus 2x. You still get your 1/2 from the outside, plus c, boom. Part D, the inside part is 3x plus 2. The derivative of that is 3. 3 is just a constant multiple off from 1, right? So that means you can multiply the 1 by 3 to get 3, multiply the outside by 1/3 to offset it. Bada bing, bada boom. The 3 gets absorbed because it's the u prime. The 1/3 carries down. You got 1 over u. Antiderivative, that's ln absolute value of u, so on and so forth. Okay, I know I'm talking fast, but I don't have time to write that down. Hopefully you can write that down into your notes and think about it more slowly yourself as needed. All right, what I'm here to do in the videos for this section is to talk about examples, primarily examples 5, 6, and 7, and I think there was one more from the homework I was going to, 21, that I was going to go over. And then I have something to say about the last 2 pages of this section. Okay, so we're going to talk about example 5, because sometimes these things don't go quite so smoothly. Page 356. And again, this is, I don't know, I like it when they get kind of like tricky like this. Again, they're just like little puzzles. just like little puzzles. Anyways, my husband and I just finished the probably some of you watched it over the holidays, the new Knives Out movie, Glass Onion thing. Anyways, like they get like that puzzle box at the beginning of the movie, and it's just like, and then you finish one puzzle, and then you get another puzzle, and you get another puzzle, and it's just like, ooh. Okay, so this integral says this: x squared plus x plus 1 over x squared plus 1 dx. All right. Now on first inspection, again, these questions, even for me, myself, if I were just given one out of the blue, I would have to think through the different options, right? So like when I look at this, I immediately noticed that the polynomials on the top and the bottom have the same, the same degree. First of all, make sure you're not getting this confused with the limit of these polynomial division things as x goes to infinity or negative infinity. This has nothing to do with like if you took the limit of this like fraction thing as x goes to infinity, right? Then you'd be like, oh yeah, top and bottom have the same degree, so it's like the ratio of the coefficients, the leading coefficients. Oh yeah, 1 over 1. Absolutely not. That has nothing to do with this. Okay, so just make sure that's not in your mind. Okay, but well, based on context clues, we know right now we're in 5.7, so we know there's going to be some kind of natural log that comes up somehow. But how could that even work, right? If I were thinking, how would I choose what my u is? Well, based on what we know about this being in the natural log section, it's probably going to be chosen based on the denominator. It's not always true. But even if we chose the numerator as our u, the derivative of that would be 2x plus 1. That's not the same thing as x squared plus 1 in the denominator. That doesn't match. It's a degree of x off. You can't do that. If you immediately chose your denominator to be the u, x squared plus 1, derivative of that is 2x. No, the top's not a constant multiple of 2x, so you would still be scratching your head. So what other tools do we have? Again, this is where we have to kind of like reach back in our creative, critical thinking math toolbox. I'd be interested to see what ideas you guys had if I was there in person, but all right, it is what it is. So spoiler, you can even see in the book, you're going to do long polynomial division. You can do synthetic division if you remember how to do that. Sure. But just remember, actually, you can't do, just kidding, you can't do synthetic division because the denominator here is not a linear binomial. Sad times. There might be like an alternate way to do synthetic division with that, but I've never done that, so I don't know. So we're gonna do, we actually need long polynomial division first. All right, so to do that, we got to take the top, x squared plus x plus 1. Remember, if there's any missing powers of x, you have to put a 0. That's not a... Okay, so like here on the outside, we're divided by x squared plus 1. We can't just put x squared plus 1. We have to put x squared plus 0x plus 1. The book doesn't do that, but okay, so x squared goes into x squared. How many times? 1 time. So this is actually, it's a very easy polynomial division problem. But so it goes in 1 time, so you're immediately already going down to the constants position. 1 times x squared is x squared. 1 times 0x is 0x. 1 times 1 is 1. Subtract this whole thing. Remember how you have to like do this. I'm just trying to imagine the moans from probably the moans that are happening right now in class. I thought we were done with this, prof. Okay, so the x squared minus x squared, that's 0. X minus 0x is x. 1 minus 1 is 0. So we're left with an x. remember the remainder goes up here. So plus, right, this x divided by the divisor, I think that's the formal name for it, x over x squared plus 1, right? So this whole thing, right, this whole thing is equivalent to that whole thing. So I'm going to rewrite it. So this is equal to the integral of 1, I'm putting this in giant brackets again. If you have more than one term, you got to put brackets, parentheses, something showing that the whole thing is your integrand all times dx. 1 plus x over x squared plus 1 dx. Okay, now how can you do this? When you have separate terms in your integral, right? Just like if you're integrating a polynomial, you can split it up. So this is the same thing as the integral of 1 dx, or even you can just write it as the integral of dx plus integral x over x squared plus 1 dx. Okay, and the integral, and honestly, I'm going to, for now, because I want you to get used to seeing this. If you see the integral sign and just a dx, I don't want you to be freaked out by that. I would ask you, what does that equal? And I'm sure there would probably be some wrong answers, right? The antiderivative of 1, it's not 0, it's not 1, it's x, right? Because if you're going backwards, the derivative, like what function's derivative is 1, would be x. This is x. It would only be plus c, but we can just do 1 plus c at the end. So x plus, all right, now we have to deal with this. But now the bottom, now in this second integral, it's pretty obvious. We're going to have to do some kind of, undoing chain rule thingy. This is our u. So u equals x squared plus 1. So du dx equals 2x. So again, we can force the pattern. We don't need to go all the way to formal use substitution because we need a 2x. We have an x. It's different by a constant multiplier. Fine. So we multiply this by 2. Multiply the outside by 1/2. Again, these together equal 1. Check. So that means our outside function. So our f of x, our outside function, what's being done to the inside function? Well, the inside function is x squared plus 1. What's being done to it, if we ignore the 2x from the du dx part, it's 1 over blop, right? So 1 over x, right? Because this 2x is the u prime part, so what's being done to it, to the x squared plus 1, it's, it's 1 over that thing in the integrand. So what's the antiderivative of 1 over something is the ln absolute value of that something. So hopefully you can go ahead and make the leap to saying, okay, the 1/2 comes down, ln absolute value of blop, x squared plus 1. Now we have a collective plus c at the very end. There we go. Yeah, that's it. Yep. Okay. Example 6. Even trickier. This is kind of going back to where I'm not going to give away why it's tricky yet. Okay, example 6. Okay, find this thing. 2x over, that line's very long, over x plus 1 quantity squared times dx. Also, I don't know if there's someone out there just thinking, oh, every time they see like x squared plus quantities x plus 1 quantity squared. Oh, but prof, what if I FOIL it out? Usually they're not going to be, so usually that's not the answer. Usually it's not going to help you to FOIL that thing out, right? Like for example here, again, let's consider, right? We can't do anything immediately to this. Besides, we have to figure out what's some kind of inside function. If we chose x plus 1, our du dx would be a 1. Is 1 a constant multiplier to 2x? No. If we made the whole denominator our inside function, the derivative of that would be 2 times x plus 2 times quantity x plus 1, which would end up being 2x plus 2, but 2x plus 2 is not a constant multiple of 2x. We cannot add 2 inside, subtract 1, or subtract 2 outside. No. That's not how it works, because adding 2 inside actually adds like 2x inside, which is going to, that's totally different than subtracting 2 outside. So you cannot do that. You can only do constant multiplier inside times reciprocal of that constant multiplier outside. Those are your only options. So either of those options, or if 2x was our inside function, true if that was 2, the denominator is not going to give you a 2. No. All right. So again, some of this is trial and error. You're going to have to just mentally go through your options, and hopefully you would come to the point where you would just kind of be like, well, I got to give up. I don't know. I'm stuck. So usually when you're stuck, that just means you have to do formal use substitution, right? So must do formal substitution. All right. So and in this case, yeah. So it's like tricky. So hopefully your inclination probably is right, that if you were to choose a u here, probably most of you would say the x plus 1, because that's being squared. Another way of thinking about it is that you could rewrite this whole integrand as 2x times x plus 1 times to the power of -2, right? And it's pretty obvious that this would be your u. Now notice, at least as it stands now, it seems like as it stands now, again, things are going to change, but it looks like your outside function's not actually 1 over blop. It's actually 1 over blop squared, which is the same thing as blop to the -1/2, which is a power rule thing, not a natural log thing. So just be careful. All right. So anyways, whatever, I'll keep that written there. So our u is going to be this. So our u is x plus 1. Oh, come on. Okay, so our du dx is just 1, which means du equals dx. Okay, now again, what we have to do is we have to substitute for formal use substitution. We're going all the way in terms of u. So right now, so rewrite everything in terms of u. So no x is allowed to remain. Okay, rewrite everything in terms of u. So our 2 times x. Well, what is x? I got to rewrite x in terms of u. I come back up here. If u is equal to x plus 1, x is equal to u minus 1, right? We just like subtract 1. So x equals u minus 1. Okay, So when I go to write this up here, this is going to be 2 times u minus 1 over x plus 1 is equal to u, so u squared dx, we already said is equal to du, so that's du. So not too bad. All right, so now we can kind of just go based on what we have here. All right, so now we need to, well, first of all, I see that 2 and I go, there's no need for that 2 to just stay in the integrand. It's 2 times that whole thing. Pull it out. And we're going to have 2 terms in this integral. So you can write it as 2 separate integrals. You can keep it written as 1 integral. Doesn't really matter. So, oh, sorry, my laptop's falling. Okay, so 2 times. Now what we're going to have to do is distribute this u squared to these 2 terms, right? You have one denominator, 2 numerator terms with a plus or minus in between. You can distribute. So u over u squared minus 1 over u squared. U over u squared, well, whatever, I'll just write it like this. U over u squared minus 1 over u squared du, which equals 2 times. And this is where you, if you want to split it up into 2 integrals, you can. It doesn't really matter. I'm just going to rewrite it like this. 2. Again, you need these, very important. Please write these parentheses. If you have 2 terms, you need the parentheses because both of them are multiplied by the du. Okay, if you don't have the parentheses there, technically it's wrong. Okay, so u over u squared is just 1 over u squared, or nope, you know what I mean, 1 over u minus 1 over u squared. Now, just for my own sake, all right, if I was here in person, I would say, well, are we going to use a natural log type answer for our integral of 1 over u squared? And hopefully you would say, no, because this is a power rule thing. You only use natural log as the integer of 1 over blop, not 1 over blop squared or blop to any other power. So I'm actually going to rewrite this as u to the negative 2, just to remind myself that this second part of the integral is going to be a reverse power rule thing. It's not going to be a okay, so we have the 2 outside, and then we have, and we're doing, so far we're doing this in terms of u. Since we don't have any bounds, it doesn't really matter when we sub back in for x, but we have to sub back in for x at some point. So integral of 1 over u is ln absolute value of u minus u to the negative 2 becomes u to the negative 1 over negative 1. Again, reverse power rule, so we're adding 1 to the numerator top and then dividing by that new exponent, all that, plus c. Now if we sub back in, our u is equal to x plus 1, right? So 2 times, doesn't really matter how we rewrite this. Sometimes they'll just go ahead and distribute the 2. So 2 ln absolute value x plus 1 is our absolute value. Minus, again, 2. Now this is minus a negative, so really that I'm just going to make that a plus. So plus 2 over, because it's u to the negative 1, so x plus 1 is just in the denominator like that, plus c. So again, we have the 2 in both of our terms. Okay, hopefully you can get that. Okay, so again, if you have an indefinite integral, you got to plug back in terms of x. If we'd had bounds, you could either choose to stay in terms of u and change your bounds to u bounds, or replug back in for x and use the old x bounds. Okay, that one's tricky. Now I'm gonna I still want to do example 7 and homework problem number 21. Those are also tricky. Again, you feel free to pause the video if you still want to like go back and, you know, look at this stuff. There's the whole There's the whole thing if you want to like pause the video and ask each other questions or something. Okay, but I'm going to go ahead and go on. Okay. Example 7. Okay, now whatever. This is kind of, again, they just want to make sure you understand all the different kinds of ways that this could be asked. Oh, actually, before we do this, really quick, the beige box in the middle of page 357, definitely I'm not writing that down, but it's good, study habit to just kind of look over that real quick. Page 257, guidelines for integration. Learn basic integration formulas. Find an integration formula that resembles all or part of the integrand, and by trial and error, find a choice of u that will make the integration conform to the formula. Okay, yeah, essentially, I like to think of it in terms of, try to find a u such that the derivative of that u is a constant multiple, is identical to or a constant multiple of something like another part of the integrand, specifically of the numerator of the integrand. Number 3, if you cannot find a u substitution that works, try altering the integrand. You might try a trig identity, multiplication and division by the same quantity. That's the same thing as like multiplying by a constant multiplier inside and by its reciprocal on the outside. Long division we just did. Addition and subtraction of the same quantity, that's going to come up later. That's going to come up, I think, and I'm going to do some difficult questions like that in 5.8. Like that, we'll come back to that. Notice the addition and subtraction of the same quantity, that can only happen within the integrand. I already said you cannot like add a constant inside the integrand and like subtract a constant outside the integrand. You cannot do anything like that inside and outside the integrand except if it's multiplying by a constant and the constant's reciprocal. And skip number 4. If you have access to computer software that will find antiderivatives symbolically, use it. No, definitely not. That is a hard no. That sounds to me like, just give up and just ask the internet or a fancy calculator. No. By the way, your normal TI calculators cannot find symbolic derivatives or integrals. The TI Nspire can. So, yeah, but they specifically on the AP and in my class, I would not let you use a calculator on something that would give you an advantage by having an Nspire versus not having an Nspire. They're very strategic about that. Anyways, example 7. Okay, dy dx. So they're just saying solve the differential equation. I'm going to say diffeq like a cool person, differential equation. Dy dx equals 1 over x times ln x. Okay, essentially you solve the differential equation. You know the derivative. You need to know the antiderivative, like with a plus c, because they don't give you an initial condition type thing. Actually, this is going to be more in chapter 6, but chapter 6 is coming up real fast in like probably a week or so in your time, and probably like a day or two in my time. But that makes me feel like we're in like a science fiction movie. Speaking of like time travel and the future and stuff, and my futures. What? No. Anyways. Okay. How we're going to actually end up thinking of solving differential equations is actually going to be separating all the y's and the x's. So we're actually going to end up rewriting it like this and rewriting the dx over here, like multiplying both sides by dx and then integrating both sides. And so the right side is literally just the normal integral that you would normally be asked, and the left side is literally just a y, right? So then it would be like y equals, and then like this thing with a plus c at the end. Technically, yes, the left would have a plus c too, but the right also has a plus c, and then you can combine them into one giant unknown plus c. Anyways, we'll do that in we'll do this in chapter 6. Right, so if this freaks you out, just ignore it for now. This is going to be in chapter 6. Okay. Okay, so essentially you're just finding the indefinite integral of this thing. So what we're really being asked is, what is this ln x dx. Okay, now this is tricky. These problems like this are like satisfying when you get the trick, and they can be very frustrating because they can lead to roadblocks and kind of like your mind starting to spin and feel like you're getting dizzy before you get the hang of them. Because notice, in this question, you have an ln x, you have it in the denominator, and you also have not just an x, but you have a 1 over x. So that kind of begs the question, and then it kind of plays with your mind with like trying to remember, well, what is the derivative of what? What is the integral of what? Well, I know ln x and 1 over x, they're like related, right? But like, which one do I choose to be my u and vice versa? Okay. Well, remember, you want to choose your u to be something such that its derivative is located in the numerator of the integral. Okay. For example, if we chose 1 over x to be our u, the derivative of 1 over x is not ln x. Nope. That's the antiderivative. The derivative of 1 over x is the same as the derivative of x to the negative 1, which would be negative 1 times x to the negative 2, which is nowhere to be found in this integral. So you would not want to choose that as your inside function. You also would not want to choose x as your inside function, because if your inside function was x, the derivative of that is just 1, but then you have another ln x hanging out there, right? No, remember, for these problems, everything has to be used up. Either everything has to be used up in terms of fitting the form of like you see the chain rule and then you do the antiderivative thing, or used up in terms of formal u substitution. Everything's rewritten in terms of u and so you can't just have like a random extra thing just hanging out there. No. So ln x has got to be our inside function, which makes sense because if this is our u is ln x, so then our du dx, the integral, the derivative of ln x is 1 over x, right? Which is perfect. So this is what 1 over x is what we need, and 1 over x is what we have. Again, what we have in the numerator is 1 over x, right? 1 over x. We have that, right? So these actually match, even though it's a little bit less obvious. So these match. All right, so we actually don't even have to do anything. This is like so easy, it's hard. So we have, it fits the form perfectly, right? But now here's a little bit, we do have to make sure we know again, okay, so what is our outside function? And then what is the antiderivative of our outside function? So our outside function, so what's being done to the ln x here? Again, this works so much better if it's interactive, but outside function f of x. So what's being done to the ln x? It's 1 over that thing, right? If our ln x is our blop, what's being done to the blop is 1 over blop. So 1 over that thing, right? So the antiderivative of our outside function, antiderivative of 1 over x, okay, let me, again, see, sometimes even my mind gets twisted. Okay, the antiderivative of 1 over x is ln x. Yes, because we're going backwards. Yes, this problem is crazy. Yeah, it's like Inception. It's like the movie, your mind can get twisted upon itself, right? So like, what's the antiderivative of 1 over x? Essentially, the derivative of what gives you 1 over x? ln x. And remember, when we do the antiderivative, we have to put the absolute value thing here, right? This antiderivative, though, actually, again, I know this is a little bit crazy. This is why, I don't know, to me, I guess this is exciting. The fact that this antiderivative is ln x, absolute value of x, has nothing to do with the fact that this u was ln x. It's completely separate. Like, isn't that kind of blow your mind? Okay. This is why I was kind of sad that this is what I'm missing in person. But I get to live the joys of this, like, burning the midnight oil, when I'm like 37 weeks pregnant. It's so fun, right? Just okay. So what does that mean? The 1 over x gets absorbed, goes away, right? Remember kind of like what we did before. I would like kind of cross this out because I'd say that gets absorbed. Okay, and then we already talked about our outside function. The antiderivative is ln absolute value of x, but really absolute value of blob, right? So hold on to your hats, folks. So our answer, so ln absolute value, but of blob plus c, right? But again, this is, right, this is like, oh no, that's not what I meant to do. This is gonna look stupid writing it out. Blop, right? Blop. And our blop, this is our blop, right? I write that out because this answer is pretty crazy. So what goes in the argument for ln here? Ln x. That goes here. Yes, that's right. It's the ln of the absolute value of ln x plus c. Okay. Whoa. That's right. Now just think back to your little, I don't know, kindergarten minds when you're just like counting and saying like 1 plus 1. Just think, wow, 12 years ago I was just trying to figure out what number comes after 12, and now I'm doing integrals and getting crazy answers like the natural log of the absolute value of the natural log of x plus the constant c. Okay, fun times. Okay, so now I'm gonna cover really quick number 21 because this is similar to this one. I know these problems tend to be tricky for people. Again, here's a little peek at like the whole thing. If you need to pause it, think about it. Okay. So now this is the homework, page 360, number 21. This is part of your homework. So you should have the solution for this, but I wanted to talk through it because notoriously every year, questions like this are just super tricky. This one's very simple. This one's actually looks a little bit less insane than the last one. It's very similar. Again, anytime where they kind of throw in an ln x and a 1 over x in the same integral, it kind of just starts your mind spinning. Again, we have to think through our options. What's our inside function, right? Well, usually in these kinds of problems, it's the denominator. But again, if x itself was u, our du dx would just be 1. And then what would we do with that ln x quantity squared? We would have nothing to do with that. So you can't do that. What if we chose our u to be 1 over x? Well, if our u is 1 over x, the derivative of that, right? That's the same thing as saying our u is equal to x to the negative 1. The derivative of that is negative x to the negative 2. That has nothing to do with ln x. So that's getting us nowhere. So we're going to have to do something with the ln x. If we chose the whole numerator to be our u, then the derivative of that would be 2 times ln x times 1 over x. Well, that's actually bad because then you would actually need an extra ln x to serve as part of your u prime. Okay, I know that gets a little heady, but right, hopefully you probably have enough intuition now to know that usually when you have something in parentheses and then it's squared, that's usually going to be your u anyways. Okay, so our u is going to be ln x, or du dx. Again, remember here, I don't get your integrals and derivatives mixed up. The derivative of ln x is 1 over x. Okay, which is perfect because we already have a 1 over x. Again, it maybe not look explicitly like that, but there's can be an implied 1 here, and you can say, oh look, there's your ln x, look, they match. So you already have it, right? You already got it. You don't even have to like change it around or do formal use substitution or anything crazy. This one's actually not hard. It's just a little bit mind-bending. Okay, now our big thing is, what is our outside function? So our outside function, oh, I don't know, where should I write this? Our outside function, well, what's being done to the ln x? It's being squared. So it's x squared. And so the antiderivative of our outside function is x cubed over 3, right? Blop cubed over 3. So that means, again, the 1 over x goes away because that gets absorbed, right? That part gets absorbed. So we have our blop cubed over 3, but we plug in our blop, which is our ln x, so we have ln x, all that cubed over 3 plus c. That's all we need, right? So we got our antiderivative, we got our x cubed plus 3, or over 3, and we just plug in our blop, which is our ln x, which is from up here. That's it. Okay, so it's not that bad. But I know those are very tricky when they throw in an ln x when you already have a 1 over x, and your mind can start spinning. All right. Oh yeah, now I was going to make some final comments about the last 2 pages of 5.7. So page 358 and 359 in your textbook. Hopefully you have those out and you're looking at them now like good students. I want you to read through example 8 and see how you can rewrite tan as sine x over cosine x to derive the antiderivative of derive the antiderivative of tangent as being negative ln of absolute value of cosine x plus c. And they have in the beige box at the top of 359, they have the integral of sine and cosine, which you already know, that's super easy. And then they have that tangent one that we just talked about deriving. They have cotangent, they have secant, and they have cosecant. Now, I think what I wrote in your notes, I obviously sine and cosine you have to know. Duh. I mean, yeah, duh. And you already know them. The others, I think it's good to know the kind of the idea behind deriving the tan and the cotan integral, if for no other reason than just to know that kind of trick that you could use trigonometric like substitution to do something like that, just generally speaking. But I wouldn't really waste my mental capacity to memorize those last 4 integrals, the integral of tan, cotan, secant, and cosecant. We are going to come up on integrals of that involve like arctan, arcsine, arc cosecant, that kind of stuff, and you will need to memorize those, you'll see. These just aren't really used. I don't remember a time when the AP has used them. I don't think I use them on anything except possibly to have a bonus where you derive the integral of tan or cotan or maybe secant or cosecant. I don't think I have either of those two because those, like example 9, it's a little complex, you can see. So just look through example 8, example 9, meh. Example 10, that's kind of meh too, because they use a trig substitution like trig identity to rewrite 1 plus tan squared x as secant squared x, and then they implement the integral of secant x. Not that important. Example 11, I would take notes on, mostly just to remember, hey, average value of a function? How do I do that again? So you should remember how to do that. The use of the integral of tangent is kind of annoying because, again, I don't really think you're going to ever have to use that. But, you can look over example 11 just to remind yourself of the average value. And that's it. Yep. Okay. Then I'll be back for more explaining in 5.8. Hope you're doing well. God bless. Godspeed. Goodbye.